Chapter 3 will be on exponential and logarithmic functions. So section 3.1 is just introducing exponential functions and their graph. Okay, so in the box they have the definition of an exponential function with the base a. So f of x equals a to the x, so x is in the exponent location. A does need to be greater than 0. If this were a negative, then the values would fluctuate up and down and would go crazy. A should not equal to 1, and that's because 1 to the x will always equal 1, which will end up being a constant function. Okay, so to the right is example 1. Example 1 says if f of x equals 4 to the x, evaluate and round to 3 decimal places. This is just to make sure you can find the button on your calculator. Okay, we won't be using a calculator on the test, but we will be using a calculator throughout this chapter. Okay, so 4 to the x, so 4 to the 2.4. Okay, on your calculator, you're probably looking for the 4 and then like the up caret, and then the 2.4. Okay, and then just put it in your calculator. It said 3 decimal places to 27.858. Okay, and just put it in your calculator. Make sure you get the same result. Okay, I'm going to do the same on this one. This is 4 to the pi. Okay, you probably have a pi button on your calculator. You just need to find it. It will give you the most exact answer possible with your calculator if you can find the pi button. Okay, and then once you put it in 3 decimal places, it's 77.880. Okay, and then one more, and this is just to make sure you can work your calculator. Okay, that's a negative 1.3. 4 to the negative 1.3, 0.165. Okay, and it should get small because a negative exponent moves the base to the denominator. So it should be a small value. Okay, those were just to make sure you could practice with your calculator. Okay, we're going to solve some really basic exponential functions using the one-to-one property. Okay, one-to-one property means I'm trying to match up the bases, because if I know the bases are equal, then the exponents must be equal. So for A, it says 4 to the 2x plus 1 equals 4 to the 7. Okay, well, because they have the exact same base, it must be true that they have the exact same exponent. So it's not that you're canceling the base, it's that you're noticing that because the bases match, the exponents match because they are equal to each other. Then I'm going to go ahead and solve it. 2x minus the 1 divide by 2, x is 3. Okay, for part B, I'm also going to use the one-to-one property. B says 5 to the x plus 1 equals 25. In order to use the one-to-one property, I need them to have matching bases. Okay, so I'm going to rewrite 25 as 5 to the second power. Okay, now they do have matching bases. Because they have matching bases, they must have matching exponents. This is the one-to-one property. So it must be true that x plus 1 is equal to 2. Minus the 1, I get x equals 1. Okay, we're going to do one more with the one-to-one property. For C, it says 1/2 to the x equals 8 to the x minus 4. Okay, there's more than one way to set up this problem. It will work in multiple ways. I normally start with the side that looks easier to rewrite in exponential form. So I'm actually going to start, I think I'm going to rewrite the 8. 8 is actually 2 to the third. 2 times 2 is 4, 4 times 2 is 8. Okay, I'm going to keep the x minus 4 in the exponent spot. I do need to put in parentheses because it's 2 to the third to the x minus 4. Okay, because I wrote the right side with a base of 2, I want the left side to also have a base of 2. Okay, so to get 1/2, I move the 2 to the bottom, so it's a negative. So this is like a negative 1. I keep the x there. 2 to the negative 1 is 1/2, but I kept the x in the exponent spot. You could have also tried to make both of the bases 1/2. That would have been another nice way to do it if you're comfortable with the fractions. Okay, according to the one-to-one property, because they have matching bases, they must have matching exponents. So it must mean that negative 1x equals 3 times x minus 4. Okay, so I got x equals 3. If you want to plug it in and check, 1/2 to the third would be 1/8. 8 to the 3 minus 4 is 8 to the negative 1, so the 8 moves to the bottom, and that would also be 1/8. Okay, for number 3, we're going to graph some exponential functions. Just to remind you that what they kind of look like, once you remember what they look like, you'll be able to graph them much more quickly. Okay, if you have completely forgotten what they look like, I'm going to make a quick little table. Okay, let me plug in 0. 2 to the 0 is 1. How about, let's plug in 2. 2 to the second power is 4. Let's plug in negative 2. Okay, 2 to the negative 2 is 1 over 2 squared. So that's going to be 1/4. So negative 2 is going to go down to 1/4. Okay, and if you remember seeing this before, they're also called exponential curves because they go up like this. And if I had done 2 to the 4th, I would have gotten an even higher number. 2 to the 5th would be higher. If I had done more negative numbers, I would have gotten even smaller fractions. So this is kind of the general shape. Another good point is also 1. 2 to the 1 is 2, and I can get that nice point there. Okay, normally 2 points is good enough for me. Okay, if I just look at this graph, the domain is from negative infinity to infinity. It has a left arrow to the right arrow. The range, okay, it's going down, 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 but it's not going to cross the x-axis, so it's not actually going to get to y equals 0, but it is going up forever. So the range is going to be from 0 to infinity. I use a parenthesis on the 0 because it's never actually going to touch the 0. Okay. Because it never actually touches the 0, there is a horizontal asymptote at y equals 0. Okay, and that's because no matter what I plug in, I cannot get a value of 0 or a negative value from this function. Okay, the y-intercept, I can see it right there, is 0, 1. Okay, and is this an increasing or decreasing exponential curve? I go from the left to the right, from the left side. This is increasing, so I would say this is increasing. Okay, for the next one, if you kind of remember the shape, you don't need to make a table. I'm going to plug in 0. 3 to the 0 is 1, which makes sense because on any of these parent functions, the y-intercept is 0, 1. If I plug in 1, 3 to the negative 1 is actually 1/3 because the negative moves the denominator to the bottom. So it looks like it's going down on the right. Let's plug in negative 1 to be sure. 3 to the negative 1 is 3 to the 1, which is 3. Okay, that's good enough because I know which side is increasing and which side is decreasing. And normally the y-intercept you can peg, and then normally if you can tell which side's going up or down, that's good enough. Okay, my domain, still negative infinity to infinity. My range is still 0 to infinity. There is still a horizontal asymptote at y equals 0, and that's always true on a basic exponential function. The y-intercept is 0, 1. Is this increasing or decreasing? If I start on the left side of the graph and I follow the graph, I'm going downhill, so the y values are decreasing. For number 4, we're going to use transformations of the graph of f of x equals 2 to the x to plot the graph. We're going to make sure to include the horizontal asymptote, and normally 2 points is a good number of points. I normally transform the y-intercept and then the 1 point where the x is 1. Okay, but I'm going to start with the horizontal asymptote. Okay, for the first graph here, let's see. In words, what's happening? It's y equals 2 to the x is the parent function. It says minus 5 at the end, which means this is going to go down 5. Okay, typically the horizontal asymptote is at y equals 0. I want to move it down 5. So it's going to move down to here. And I'm going to go ahead and draw that in because it's going to help me make sure that my curve is going in the correct way. Okay, now I'm going to use the y-intercept. Okay, normally 2 to the 0 is 1. So 0, 1 is normally my y-intercept. I'm going to move it down 5 spaces. 1, 2, 3, 4. Now it's right here. Or I can think it should be 0, 1 from the horizontal asymptote. Okay, and then normally if I plug in 2 to the 1, 1, 2, I normally get a point right here. Okay, I can move that point down 1 or down 5. It'll go here. Or I can rethink of this as my x-axis and make this 0, 1 from the horizontal asymptote, make this 1, 2 from the horizontal asymptote. Okay, either way, this is enough information for me to tell that it's going down on the left side and it's increasing on the right side. Okay, and then that's a good graph. 2 points is a wonderful graph. Okay, I'm going to use transformations for the next one again. 2 to the x was the parent function. So if I make this x minus 2, this is like parentheses, this is going to the right 2. Okay, so if my horizontal asymptote was at y equals 0, if I move it to the right 2, it's still at y equals 0. Okay, so I do know that to be true. Okay, if I take my y-intercept is normally 0, 1. If I move it to the right 2, it's going to go over here. Okay, normally 2 to the 1 is 2, so normally I have a nice point here. If I move that to the right 2, I have a point here. Okay, I know this has to go down towards my horizontal asymptote, and then the other side must be increasing. Okay, for the next one, y equals 2 to the x is my parent function, so if I change that to a negative x, the x is changing signs. Since the x is changing from positive to negative, it's actually going across the y-axis. So this is reflecting across the y-axis. So the horizontal asymptote is still going to be at y equals 0, because if I flip that over the y-axis, it looks exactly the same. Okay, let's consider. My 0, 1 is normally my y-intercept. If I flip that over the y-axis, it stays right there. Okay, if I plug in a 1, I normally get 2 to the 1 is 2, but I want to reflect that across the y-axis, so instead of being on the right side, now it's on the left side. Okay, so my graph is actually going to go down on the right and up on the left because I reflected it across the y-axis, so it's flipping. Okay, the last transformation of y equals 2 to the x, there's a negative in front, so the y values are changing from positive and negative. Okay, so it's reflecting across the x-axis. Okay, my horizontal asymptote does not move because if I flip that across the x-axis, I am on the x-axis. Okay, now normally my y-intercept is at 0, 1, but I want to reflect that across the x-axis. So now it's going to be down here. Normally, if I plug in 2 to the 1, I get 2. If I reflect that across the y-axis, now that's down here. Okay, and that's enough for me to sketch it. It must be going towards the horizontal asymptote here and going this way from here. The last topic they're going to introduce in this section is formulas for compound interest. So anytime you think of the exponential model, you should be thinking of accruing interest in your account. Okay, they have 2 formulas they're going to show you. Okay, it says after T years, so that's how long your money's in the account, the balance A in the account with principal P, the principal is going to be the amount of money you initially put in. Okay, if you invested $100 when you were 6 years old, how much is it worth now that you are 16 years old? The annual interest rate, R, should be in decimal form, and it's given by 2 formulas depending how the bank calculates them. Okay, the first one is for n compoundings per year. That means maybe they calculate your interest quarterly, maybe they do it once a year, maybe they do it twice a year, maybe they do it every month. It's A, that's the amount of the account, equals the principal times 1 plus decimal rate over the number of compounding times NT. Okay, continuous compounding means like every second of the day they are calculating your interest, and you're accruing it on your new interest, and it keeps calculating and calculating and calculating. Generally, you want to think the more times they compounded a year, the more money I'm going to earn. Okay, we're going to try it a couple ways. Okay, the first one, let's see. You invest $20,000. Okay, that's the amount you're putting in. That's your principal. Your annual rate, that should say of 5%. So that's my rate. As a decimal, 5% would be 0.05. Okay, find the balance after 5 years. Okay, 5 years is going to be my time. for each type of compounding. Okay, and then they're going to give you 3 scenarios. Okay, the first scenario is quarterly. Quarterly, you divide the year into 4 pieces, so it's going to be compounded 4 times a year. Okay, and then we'll see how much money you would make after 5 years. Okay, I'm just going to plug it in the formula. Okay, and I'm going to plug it in the formula, and then you're going to put it in your calculator. And you're going to be really careful with the parentheses and stuff. Okay, it says A equals P. I'm using the first formula because it's n compoundings per year. What is P? P is 20,000. 1 plus, what's R? R is my rate as a decimal, 0.05 over n compoundings a year, so 4, raised to the n times t. What's t? 5 years. Okay, so I basically have 20,000 times 1 plus 0.05 over 4 raised to the 20th power. Okay, you're going to try to put this in your calculator. You probably need parentheses around the 4 times 5. You might need parentheses around the fraction. You might need to do these piece by piece. But if you've done it correctly, you should get $25,640.74. Okay, which is pretty good. In 5 years, you've earned more than $5,000 in interest. Okay, play with your calculator until you get that amount. Okay, we're going to try to do the same calculation, but this time we're doing it monthly. Okay, if we do it each month in a year, there are 12 months in a year, which means that 12 times they're going to compound your interest. Okay, same formula though. So A equals, my principal was 20,000 because that's my initial investment. 1 plus, my interest rate is still 0.05. We're just seeing what changes if we compound it more frequently. Now it's over 12 because I'm going to compound 12 times. And then 12 times 5 because we're doing this for 5 years, so really to the 60th power. Okay. Try to figure out how to calculate this. Play with the parentheses or maybe do each piece separately. But you should get the result of $25,667.17. Okay, so that earned you a little more money if they compound it more frequently. Not a ton, 30-something dollars, but not nothing. Okay, and then the last scenario is if they are continuously compounding it. Okay, if they are continuously compounding it, I'm using a totally different formula. I'm using A equals PE to the RT. Okay, I'm going to go ahead and plug this in. Let's see, A equals, my principal is 20,000 still. E is a constant, it's 2.7 something. It's on your calculator, so you're going to have to search for it. What is R? My rate is still 0.05. And how many years? 5 years. Okay, and just like before, you have to play with the parentheses. You might need to do the 0.05 times 5 first. Okay, and you need to look for the E button on your calculator. The E button is normally associated with the LN, the natural log button. So if you can find the LN button, the E might be hidden above it or vice versa. Okay, plug it in your calculator. Okay, we're going for $25,680.51. Okay, which is a little bit more than if they compounded it 12 times a year. Not a lot, but you know, it is money. Okay, and if you're wondering about the rounding issues, because some of these should have rounded up, your bank generally does not round up. They don't want to give you the extra penny. If you round up because you're a mathematician, that's fine. I'll mark that correct. If you don't round up because you're a banker, you can leave it the way I have it.